Awesome. Okay. So just have 9 questions to do. Or do you guys have any questions? I guess we're supposed to go over also the homework. Did you guys
Yeah,
have...
I don't.
You mean the homework for this coming? And we're not supposed to do the one for this Saturday, right?
No, the individual preparation, there's a little
Yeah,
bit that we're supposed to do.
I didn't have any questions with that.
Okay.
Yeah, I didn't.
And I guess it was good just to kind of read over that and watch that. Did you guys watch the tutorial videos as well?
I watched.
I did not.
Yeah, I watched both of them. I find the one with the guy at the chalkboard is a lot more beneficial than the instructor's one.
Yeah, I agree. Alrighty, so for the questions, starting with number 3, it says, when taking samples of n when n equals 5, what was the shape of the distribution of means histogram when the parent population is right skewed? So from what I remember, the distribution of means, it always comes out to be a normal distribution. That's from what I remember, so I could be wrong on that.
It seemed like all the answers were normal tonight for the questions.
Yeah, on the homework. Well, the preparation.
Yeah.
We had to differentiate between the two, large numbers and was it the central? The other one was the central. I forget what they called it. The central limit theorem and the law of large numbers.
Oh, that's right. So, because like the larger the number, the more proportional your distribution becomes.
It says, as the sample size n increases, the sample mean x with something over it draws closer to the mean population.
Okay. I'm guessing with a number that small, would the mean distribution also be right skewed?
Well, we do that calculation where you you take the. Actually, we don't. I don't know if we have all the details to be able to do what they were doing in the lesson. That calculation with standard deviation of the distribution of sample means equals the standard deviation of the parent population divided by the square root of the sample size. I don't think we're using that for this question.
Okay. I'm just going back on the reading real quick and just seeing where I can find that real quick.
Come down there.
I'm looking at the summary of the video, like the very end of the video that the instructor did.
Yeah.
Okay. Well,
we know as the sample size gets bigger, it draws closer to the mean, and also as the n increases or becomes larger, it also the sample mean becomes approximately normal. So
So I think for number 3 it would be skewed right because the parent population is also right skewed and you only have a number of 5. So therefore it would make the distribution of the mean skewed right. But
I would agree with that from the reading.
then from number 4, since it's 100, even though it's right skewed, it would still give a normal distribution of means. And then for number 5, it would also be a normal because the parent population is also normally distributed.
Yeah. Does 100 count as a large number?
Well, he was using 1,000 in the examples.
Yeah, the TA kind of.
So I don't know if 100 is a big enough number.
Well,
Well, we know it's a lot bigger than 5, so I don't know. It's
yeah,
20.
that's what I was about to say. I would say normal on 4 and 5 then. And skewed right. I agree with all that.
Okay. What do you say, Jason?
I it makes most sense to me. It's yeah, I think so.
Okay, so for number 3, we'll put skewed right.
Yep.
For number 4, because the parent population is right skewed, but the number is large, we'll go with a normal distribution of means. And then number 5, it would just be normal again because the parent population is also normal distributed, and then you also have a big number.
Yep.
Okay.
6 is all the above.
Oh,
Okay.
it's all of them for 6?
No, 6 is, yeah, you can choose more than one choice. You have to. It's like one of those questions where it has to be more than one, but it's not all of them.
Uh-huh.
So, when would the distribution of means be normally distributed? Choose all the correct responses. So it's not the first one. The sample size is small. Data is drawn from a population that is normally distributed and the size is large. That one, the second one on 6, I think, should be checked.
Yep.
Then data are drawn from a population to the right skew. The sample size is small. No. And data is drawn from a population to the right skewed and the sample size is large. So I think it's going to be the second and the fourth for number 6.
So basically, for the distribution of means to work, you have to have a large sample size.
Yeah. I think it is drawn from population.
I didn't mention, well, I got to go back to it again. It was mentioning the central theorem. When it's large, it becomes normal.
Right.
So it's talking about, right? The central. No, that's the next question. Okay, distribution of means to be normally distributed. Distribution of mean.
Well then, so going off of what we figured out for 3, 4, and 5, wouldn't the first check be also checked because the population is normally distributed, but the sample size is small? But that would still give you a normally distributed distribution of means.
Here, let me
Because,
read. Let me read you what it says about the distribution of the sample means. It says when the distribution of the sample means x with that squiggle over the top is normal, when the parent population is normal, and or that when the sample size is large.
so if the parent population is normal, then no matter how big the sample size is, that means that your distribution of means will also be normal because the data is normal. Correct?
Yeah. So or when it's
Yeah.
large.
So that means that the first 2 will be checked and then the third won't be checked.
For 6.
Yeah. Because the first one says data are drawn from a population that is normally distributed and the sample size is small. So even though the sample size is small, it does say that it's normally distributed, so wouldn't that make the distribution of means also be normally distributed? That's what we were saying on 3, 4, and 5.
Yeah, I see exactly what you're saying. I'm reading right now.
Okay, yeah, I'm gonna go back and do that.
We know it's not the third one for 6. That's all.
Yeah, the third one's out.
That's for sure. As a sample size of one distribution.
That's so.
It almost seems to me on number, let's see, number 3, or well, with a small sample, it seems to me that you could get anything. Like you could get skewed right, skewed left, or central, because your small sample could be so far off from your actual mean. Does that make sense?
Yeah.
So I don't understand.
I guess with number 3, the reason why we would go skewed right is just because the parent population is right skewed. So
Okay,
more
so
often than not, you're going to get a skewed right distribution of mean.
Well, we're doing
okay,
that because the distribution sample mean is skewed right because it's a small population. But it says when it's normal, then or the sample size is normal, then the distribution of the sample is going to be normal. So it seems like it's an outlier, and it seems like that.
Okay.
So I agree with staying with A or the first choice in 3.
yeah, I agree with that. But what about the first one on number 6? Data is drawn from population is normally distributed with a sample size is small.
It's got to be.
If 3 makes sense, then that makes sense.
Yeah. And then we have another one, the same as the second choice for 6. It says it's normally distributed. It doesn't really matter if it's a small or a large size. So that one should be checked. And then the population is right skewed and the sample size is large. So I think one for 6, A, B, and D. But
Yeah. But I mean, going off of what Kelly was saying too, I mean, with only having a small sample size, it could be that the distribution of means wouldn't be normally distributed just because we have such a small. Oh man, I don't know.
it defines it as normally distributed, even though the sample size is small for the first one and 6.
hmm Okay, well let's just go with that for right now, I guess.
All right,
So A, B, and D, that's what I'm going with.
Yeah.
Yeah.
at this point, unless we continue to, well, let's move on and we can come back to it.
Okay, number 7. Which of the following gives the best explanation of the central limit theorem? If one parent population from which the data was drawn is normally distributed, then the sample mean will follow a normal distribution for bell-shaped data. Approximately 68% of the data will be within one standard deviation of the mean, with 95% of the data being within 2 of the mean, and 99.7% of the data will be within 3 standard deviations. If the sample size is large, the simple mean will be close to the population mean. If the sample size is large, the shape and sampling distribution of the sample mean will be approximately normal. More reading.
So the definition they give us of the central limit theorem is as the sample size n increases and becomes large, the distribution of the sample mean becomes approximately normal.
That would be the last choice.
But they're using x, they're not using n. So in the last one?
Sample size large. I would say, yeah.
It just seems like this question is like we're gonna overanalyze ourselves into choosing the wrong answer.
So I just looked it up real quick. It says that the central limit theorem states that given certain conditions, their arithmetic mean of a sufficiently large number of iterates or independent random variables, each with a well-defined expected value and well-defined variance, will be approximately normal distributed regardless of the, hold on, where'd it go? Regardless of the underlying distribution. That really doesn't make much sense to me.
I think it's the second choice for 7.
For bell-shaped data, that one.
Yeah.
Is it in the same order when I read it on you guys'?
Yeah.
Yes.
So we're going with the second one?
I think it's the second.
Okay.
Because everything else seems like it's grabbing things from other
theories.
Yep.
Okay, fair enough. Let's go with that one. Alright, so number 8 says let x be a random variable with a population mean of 10 and population standard deviation of 6. Suppose the sample size of 36 is drawn from this population. What is the mean of distribution of sample means? So, if I remember right, there's a handy-dandy little formula we use to find this.
Yeah, I'm looking for it.
I'm looking for that right now.
There's green berries.
Is standard deviation divided by the square root of sample size?
Oh yeah, I'm pretty sure that was it.
Yeah.
But do we not use the mean then?
We should.
Well, isn't it's? I don't know all these things. You got the. So are we using the one with the square root on the bottom? That.
Yeah, that's the square root of the standard deviation. Or I'm sorry, the square root of the number, the sample size.
The symbols are supposed to make it easier, but I don't always remember what the symbols stand for. Anyway.
Actually, that's the standard deviation of the sample, so that's going to be number 9 that I just read. That's the formula for number 9. So, standard deviation divided by the square root of the sample.
Well, wouldn't that just be 1?
6. Yeah, be 1. Says the 3 decimal places.
1.000.
Oh yeah.
What is the mean of the distribution of sample means?
Is that a better one?
So I'm looking at where they.
Let's see. Mama.
I'm looking for it. I'm not coming upon it yet.
Review population 10 standard deviation. Random variable with population. Okay, look at this. All right, I'm just trying to get this theorem here so I can look at it on a different screen.
When I was looking for that formula just now, I actually kind of came across something that's a little interesting. So I'm just going to share my screen with you guys just so you can see.
Okay.
Um, so right here, so can you see this?
Yes.
It
Yeah.
says that we have a population that's like non-normal at all, and the distribution size of the sample mean equals 5, so they're only taking sample size of 5, and this is what they got. So that's almost like a normal distribution. And then when they get 25, it's even more normally distributed. So maybe it really doesn't matter about the population. I don't know
Wait, yeah. So I'm looking at the reading, and they took kind of the same thing with the bus. Did you guys read that part? Like the amount of time passengers spend on a bus. So they have two questions, and it's almost identical to what we're answering. The first one with the mean, it doesn't even show a formula or anything. They just took the mean from the question, and then on the second question, they have the formula that I used to get number
You're saying that we're going to use the
9.
formula for number 10
9,
for 9. Okay.
right? Because we're looking for the standard deviation there.
right.
But in the reading, I don't see any formula. They just took it straight down. 8.7 to 8.7 is what it is.
Deviation 6.
Oh, okay. I just realized, sorry, on that thing that I showed you guys. So that was in regards to the sample mean, not to the distribution of the means. Just to clear that up, sorry.
Yeah.
Okay, guys, hold on one sec. I actually have a really good friend who's really good at this. I'm gonna ask her a few questions real quick.
Okay.
Deviation is 36, 42, 30. Sample. N is greater than 30. I'm just looking at number 10 while we're waiting. So,
Oh, okay.
um,
Here this is. Size is large.
I think the answer to number 10 would be normal.
Yeah. So that right there answers our question of if 100 is a large sample
Just
size.
say 30 is large. They're
Yeah.
defining 30 is large. And what theorem for 11?
Law of large numbers. Right? Not the central limit.
Also, the central limit theorem says that as the n increases, becomes large, the distribution becomes normal. I think it's a central limit theorem. Is that one of the answers? I don't know. To look back. Central limit theorem. The law of large numbers says that as the sample n increases, the sample mean draws closer to the population. Sorry, draws closer to the population mean. So I think it's number 11 would be central limit theorem.
Okay. Central.
So I think the only one we were still uncertain of is 8.
Just a second. My 3-year-old went back upstairs.
All right, let's look. Yeah, I can't get these things bigger on my screen.
I cannot find anything on this. No formula, at least.
We can't use the standard deviation of a distribution of sample means equals the standard deviation of the parent population divided by the square root of the sample size.
Okay, I'm back.
What'd she say?
So she's a math major, so she's super smart. So a couple things. We were right on 3 through 5. So like with the way we figured that out, like that's completely correct.
Okay.
As well as with number 6, it's ABD. But however, number 7, the central limit theorem, is not the second one. It's actually the last one, where the sample size is large. The shape of the sampling distribution of the sample mean will be approximately normal, is what that one states.
Sample size.
It just messes me up because it uses the x instead of the n, because it says in the central limit theorem, it says as the sample size n increases. It doesn't mention x anywhere in that.
I must have it backwards because that sounds like the law of large numbers to me.
What is the law of large numbers? What does that state?
Let me look that one back up. I was just reading the central limit theorem.
Because those two are kind of almost the same thing in my mind.
Yeah.
Well, they were saying, the instructor was saying that it's important later on in the semester to be able to differentiate between those two theorems, large numbers in the central limit.
On the
Theorem.
summary on the reading, it says the distribution of sample means is normal when X is normally distributed, or when, thanks to the central limit theorem, our sample size is large. And then the law of large numbers states that the sample size gets larger, the sample mean will get closer to the population mean. Distribution of the sample means.
Can you say the central limit theorem one more time?
Yeah, the distribution of sample means is normal when X is normally distributed, or when our sample size is large.
Yeah, that's exactly what the fourth one says.
Okay.
Okay.
Yeah.
I just was reading the key points definition, sounded a little different, that's all.
Okay.
And then for number 8, I don't know if I kind of overheard you guys saying that it's just mu, correct?
Just what?
So number 8 is just the mean. The mean of the distribution of sample means is just the mean.
That's what I'm gathering from the reading, because it never gives you a formula or anything to figure.
Yeah, you're correct on that. It's number 8 is 10. And then number 9 is yeah, we just use that formula that we found, where you take the standard deviation divided by the square root of the number. So that just comes out to 1.000. And then number 10. So what she said is if the sample size is any bigger than 30, then your distribution of the sample mean is always going to be normal.
Yeah, we discussed that while you were gone. We got
Awesome.
the same thing.
We discussed 11 and said it was central limit theorem, but
Yep, that's right. That is
Submit.
theorem. So that should about do it, boys.
Okay, I'm going to run through them again because I'm scared again. Number 3, skewed right. 4 normal, 5 normal, 6 ABD, 7 D, 8 10, 9 1, 10 normal, 11 central limit.
you have to put 3 decimals. Yeah, after 9 you have
Yeah,
to.
I did 1.000.
So, because if it's not set up the way they say, even if you get 1, even if you put 1 without the trailing zeros, you're not going to get it right.
Yep.
All right, I'm submitting.
Okay, I'm too.
100%, guys. Good job.
Yay, done.
Good
Okay.
job.
What?
All right,
Wow.
guys.
Let's
I
do it
will
again.
see you guys on Thursday.
Yep.
Yeah, see you Thursday, guys.
Happy birthday tomorrow.
Hey,
Yeah, happy
thanks,
birthday.
Jason. Appreciate that. I'm getting to be old.
You'll catch up to me sometime.
I'm turning 25 tomorrow. Can't believe it.
25.
Yeah.
Congratulations. We'll see ya.
It's so hard to get here. Okay. Have a good night.